All right, so we're going to finish up our discussion on enzymes now. So we've talked about all these aspects of enzymes already. And then the next thing I want to talk about is how the enzyme binds very specifically to a substrate. So the definition of a substrate is it's the reactants that bind to the enzyme. It's what the enzyme binds to help catalyze and accelerate, speed up the reaction. This is very specific. So you pretty much need a different enzyme for every different substrate or every different reaction. So again, we talked a little bit earlier about cascade, a reaction cascade, multiple steps. Each step would need a different enzyme because what's fitting in that enzyme's active site is different along the way, right? And so we know this because there are a lot of people who are lactose intolerant, and that means that they do not produce a functional enzyme that can break down the enzyme lactose or the sugar lactose. However, pretty much everyone can still break down sucrose, whether you're lactose intolerant. This is important because if you couldn't break down sucrose, you probably are having a hard time generating energy from calories, right? So this is lactose, these two sugars together. This is sucrose. They're not that different, and yet they are so specific that you need a different enzyme to break down lactose, a la lactase breaks down lactose, or sucrose, sucrase, breaks down sucrose, right? Ase usually indicates an enzyme, and then the prefix to that is what it breaks down. So sucrase breaks down sucrose, lactase breaks down lactose. But if your gene for the lactase enzyme does not create the perfectly folded functional enzyme, you can't break down lactose, or at least not as well, and that's why you get an upset stomach if you drink too much dairy products. All right, so, but again, very specific because sucrase cannot break down lactose and vice versa. Different enzyme for each reaction, pretty much. All right. So which of the following best describes why enzymes are very specific? Because each enzyme folds in such a way that only specific substrates fit into the active site. Amino acids lining the active site provide favorable interactions with specific substrates but not others. Both of the above or none of the above? Well, the answer is both of the above. It's because this active site is the perfect fit for the substrate, and it's because the interactions with the substrate are also perfect. So let's think about this for a second here. So here's an enzyme. This would be an active site where the substrate's going to bind. Oftentimes, it even creates an induced fit. So once the active site binds, it causes the enzyme to even change conformation and almost close in on it. So this is kind of like the key in the keyhole. It's a perfect fit, and it even kind of helps lock the enzyme locks around the substrate to help it bind. All right, so that's the perfect fit part. But a different substrate is going to have a different size, and it's not going to fit as well. And then we also have the interactions. So what I'm trying to show here, so let's assume this is the edge of our enzyme, right? So the enzyme is this whole folded thing here. I haven't shown the side chains or anything like that. But this would be the active site, and this is my substrate, RUBP, right? This molecule here is what's binding in the active site. So now I've just kind of shown some of the side chains, right? So these are the amino acid side chains that are sticking out in the active site. And hopefully you can see how this fits pretty well in the active site. I know this is a cartoon diagram, but the substrate fits in this active site. And also we have perfect interactions. I know that this carbon double bond oxygen here, that has a negative dipole here. Well, OH on my substrate has a positive dipole here. There's a perfect interaction for a hydrogen bond here. Same here. Negative dipole, positive dipole, perfect interaction. A basic amino acid with its positive side chain, well, that interacts with the negative phosphate group of the negatively charged oxygen here, ionic bond. Same over here, right? Another hydrogen bond interaction. So not only does the substrate fit perfectly in there, but the protein folds in such a perfect way that the side chains are left there to interact with this substrate almost perfectly. Right? That's why it's very specific, though, because a different substrate, a different molecule is not going to have the exact same size, and a different molecule is not going to have these exact same interactions. All right, so let's go back for a second. This was a question we started in the very first video. Which property below is a false statement about enzymes? Enzymes are very specific. Enzymes determine whether a reaction is exergonic or endergonic. Enzymes facilitate rapid reactions under physiological conditions. by lowering the energy of activation, enzymes are not used up by the reaction, or enzymes can stabilize transition states during progression from reactants to products. Which one of those is false? Well, hopefully by now you've figured out that B is false. Enzymes lower the energy of activation. They speed up the reaction by doing so. They make it physiologically possible to make reactions happen more quickly without increasing temperature, reactants, etc., stabilizing transition states, and they bind very specific. We've learned all that. They do not determine whether a reaction is exergonic or endergonic. They can help speed up by lowering the energy of activation, but they cannot make an endergonic reaction exergonic. All right, so let's talk a little bit about inhibition. So if you wanted to regulate an enzyme, there are different ways that can happen. And this can be natural regulation by a cell, right? So a cell wanting to regulate an enzyme, make sure it's on and active sometimes and off other times. This can also be through like trying to have a drug or a medicine. So maybe you have to block an enzyme so that you can really prevent a disease or mechanism from happening. So you need to block an enzyme from doing its job. Maybe it's doing its job too well or at the wrong time. All right, so let's think through this inhibition. Here's a cartoon diagram of my enzyme. This is the substrate binding site. So the substrate fits in there pretty well, etc. Well, one type of inhibition is called competitive inhibition. Competitive inhibition occurs when the inhibitor, shown here in black, basically binds to the same site as the substrate would. This means that it's competitively inhibiting the substrate from being able to bind there. Now, what would you expect the nature of the competitive inhibitor to be? Well, it would have to look quite similar, but not exact to the substrate. So it has to be able to bind with the same interactions in the same space, but basically by preventing the substrate from binding, prevent the reaction from occurring. Right? So take-home message, a competitive inhibitor binds in the active site, and in doing so, it has to look quite similar to the substrate that would normally bind it. On the other hand, we have non-competitive inhibition. Right? Excuse me. Non-competitive inhibition is when you have an inhibitor bind to a different site on the enzyme, and we call this different site an allosteric site. Now we know that when something binds to a protein, that binding can change its fold and therefore change its function. But this is a non-competitive inhibitor because it's not competing for the same binding site, it has a separate binding site. But in binding to the allosteric site, it changes the fold of the protein, and now the substrate doesn't fit in the active site because that fold is changed, right? So in this way, it's preventing or inhibiting the enzyme from doing its job by causing the change of fold. We know that change fold, change function, right? So competitive inhibitors bind to the active site, compete for the same binding site. Non-competitive inhibitors bind to an allosteric site, and in doing so change the fold, and now the substrate no longer fits into the active site like it should. Okay. And this is kind of my diagram of that allosteric site. So this is the active site with it bound, right? When an allosteric inhibitor, that non-competitive inhibitor, binds somewhere else, it's still going to change the fold even at this distant site. So even though it bound here, it changed the fold all the way over here in that folded protein. And now if that fold is changed, not only does the substrate no longer fit, but those interactions don't line up right? So here we might still have an ionic bond, but this hydrogen bond no longer, that's near a nonpolar bond. It's not going to work, right? These are further apart from each other. These are not lining up. So not only does it not fit, but the interactions have been lost. So that's how that allosteric site, when the non-competitive inhibitor binds, can cause the substrate to be unable to bind. It changes the fold, therefore changes those interactions. All right, the last thing I want to talk about for this asynchronous class is feedback inhibition. This is also known as the end product inhibition. All right, so I want you to think about what's happening here carefully as we go through it. So what we have here is a metabolic process. This is where we're starting with a particular substrate, right? And in this case, I know this is cartoonish, but the substrate looks like this triangle. The enzyme, it's going to bind into enzyme 1's active site, and in doing so, it's going to help accelerate the conversion of this triangle to a new product, shown here by this kind of purple rectangle. Right? Well, the purple rectangle will then be able to fit in enzyme 2's active site, and that changes it to here, and then that has its own enzyme to change it to the end product. So the whole point of this whole cascade, enzymatic cascade, metabolic process, is to take something that we start with and get an end product that the body needs. So this might be something we can eat, and this is what our body has to turn it into that the cell needs. Right? Now, let's think about this for a second. There's a lot of reactions going on here. Right? And if I have a lot of substrate, I can make a lot of product. But when do I want this set of reactions going? Or when do I want them occurring? Well, I want them occurring when I need this end product, right? When the body doesn't have enough and needs this. So when there's not enough of this, I want these enzymes to be active and converting the triangle to this rectangle, the rectangle to this kind of blue blob, and then making the end product. When do I want this not to work? Well, I want this not happening when I already have enough of the end product. So I want this to turn off when there is enough or too much end product. So what can happen is the first enzyme here, the very first part here, has an allosteric site that the end product binds to. Now this has to be an allosteric site because the end product doesn't look the same as the beginning. If it did, there was no point in this whole set of reactions. Right? So it has to bind to an allosteric site. But when it binds to the allosteric site, that's non-competitive inhibition. It changes the fold, and now my substrate no longer binds. So the end product is inhibiting the first enzyme in this reaction to stop the process. This should make sense. Because if I'm using up this end product, if the cell needs it and it doesn't have enough, doesn't have enough, as soon as this end product's made, it's going to be used for whatever the cell needs it for. And therefore, I don't have any extra to bind and inhibit this. So if I don't have enough, I have nothing to inhibit it, this is going to keep reacting. But as soon as I have excess, right, the cell's already used all it needs, now we're just building this up. Now I have extra end product, I have some left over to come back, bind, and now I'm going to turn this off. I'm going to block the first enzyme, and no longer are any of these pathways, right? So if I don't convert the triangle into a rectangle, there's nothing for enzyme 2 to do. And if that doesn't get converted here, there's nothing for enzyme 3 to do. So by inhibiting the very first step, I've inhibited this whole process. And by using the end product to do that, I'm inhibiting it only when I have extra end product. And then if I start to use this up, well, this is going to fall off and get used up as well. And now the enzyme's free and I'm going to make more. So as soon as I don't have enough, I need more. There's nothing to inhibit it. We get more made. As soon as there's extra built up, my end product starts to build up and I have some available for this allosteric inhibition, and I stop it. And as soon as I run out again, that will fall off and be used up, and I'll open it up again. So the body does this very smartly. In a long metabolic process, it'll use the end product or something near it. The buildup of it will be the allosteric non-competitive inhibitor that stops. And you want to stop an early step. There's no point in stopping enzyme 3 because then I just build up a whole bunch of this. I want to stop an early step. So let's take a look at this here. This is an actual synthesis pathway, making tryptophan. Tryptophan is an amino acid that the cell needs. So it starts with coarse mate, and then this enzyme, anthranilate synthase, turns it into anthranilate. And then this enzyme turns it into this enzyme turns it into this, and in this 6-step process, we end up with tryptophan. So this is where we start, this is what we end up with, and this is what the cell needs, tryptophan. So my question for you is, which of these would be a good inhibitor, and which enzyme should we inhibit? All right, the take-home message and what you need to know is that the final product is always going to be the inhibitor, because when I have extra tryptophan, I'm going to use that to non-competitively inhibit an enzyme. And you always want to inhibit one of the earliest enzymes. There's no point in inhibiting this halfway through. So tryptophan would be my inhibitor, and I would inhibit step 1, the anthranilate synthase. That's the enzyme I would inhibit. So this enzyme is going to have an active site where corsmate binds and gets the energy of activation is lowered to help it speed up its turning into anthranilate. And it's also going to have a second binding site where tryptophan binds allosterically, And when tryptophan's available, I have too much of it, it's going to bind to anthranilate synthase, changing its fold. Now corismate doesn't bind. We stop this whole process. As soon as the body has used up all the tryptophan it has and needs more, well, I have nothing left to inhibit this, and now this is going to be active. Corismate will fit in the active site because there's no allosteric inhibition, and then we'll get more being made, and back and forth, right? So when you see a pathway, just know that the end product is a very good allosteric inhibitor, and you always want to inhibit one of the early steps along the way. In this way, the pathway is only happening when the cell needs more of this, and when it has too much of this, it stops it. All right, thank you very much. This is where we'll start in class, talking about Chapter 7 and basically cellular respiration. Thank you.